I am also very excited for today's session because it is going to be about space, and we are going to discuss about the recent achievement that India has done in this field of space and technology. And I'm sure you kids would extremely love this session because we have our expert uh, from ISRO itself who is going to take us through the mission details and going to explain the topic in simple terms that kids can understand. Before we begin, this is a webinar session, which means you will not be able to speak back to us. But that being said, whenever you have a question, please put it in the chat or in the Q&A section. And as and when the time permits, I would curate the questions and get it clarified with our expert here. And our moderators are also there, and they would also be helping you with your answers. Okay, great. And Playto Talks, warm welcome to Playto Talks. Playto Talks is a series of talks that Playto Labs is organizing with experts at technology. And the main motive behind arranging a Playto Talk is to help you kids understand what is happening in the current technology and how technology is advancing in the current pace, and how you can also learn and understand the current technology from the experts itself in a simple way that you will be able to understand and gain insights upon. Okay. On today's session, we are going to discuss about Chandrayaan 3. So the topic is everything kids need to know about Chandrayaan 3. And to give you a few facts about Chandrayaan 3, so Chandrayaan 3 is a follow-up mission from Chandrayaan 2, where we wanted to land upon moon, especially in the South Pole. And do you children know why we wanted to land on South Pole? If yes, can you reply in chat if you know the answer? Why do we want to land on the South Pole? Yes, we want to explore it and so on. So in Chandrayaan 2, Chandrayaan 2 has had three things. One is an orbiter, a lander, and a rover. Although due to a software malfunctioning, we couldn't land properly, but the orbiter is still functional. And we have received data of, presence of water molecules in South Pole. That is why, we wanted to land on South Pole to explore that in detail, because finding water in space is the next big thing, right? Not only on colonization, it also helps us to prepare rocket fuel, etc. So it is going to be a one of a kind discovery. That is why it is very important for us to be successful at Chandrayaan 3. And Chandrayaan 3 is one of our achievement and a proud moment for all of our Indians. So today we are going to see more details about this mission from Mr. Shiju G Thomas. So Mr. Shiju G Thomas is a scientist and head of staging working at ISRO, and he's also a senior scientist. And he's also a father of a young child who is very, inquisitive and interested in learning about technology. So he's going to talk to all of you today like his own child, and he's going to explain about the mission details as well as the space technology that is used in the Chandrayaan 3. So like you, I'm very happy to welcome Mr. Shiju Thomas for the session today. Good morning, sir. Are you with us, sir?
Yeah, good morning, Vasant. Is my
Good morning,
video
sir. How
visible?
are you doing, sir?
Is my video visible and audio good?
Yes, sir. It's audible, sir.
Thank you. Thank you. So good morning, kids. Good morning, children. So today we are going to talk about Chandrayaan 3. So shall we start? Okay. First, I will share my screen. Hope the screen is visible to all.
Yes, sir. It is visible. Yeah.
Yeah. So let's begin. So today we are going to discuss the journey of this particular small robot called Vikram from a place in Earth to a place in Moon. So how it went and why we went and what we did there, this is going to be the gist of the topic today. So don't worry, this will be the only slide without any pictures in it. Okay. So just to give the outline of the presentation today. So first we will understand how the Earth-Moon system works, so that we will have a better understanding of the later part of the presentation by giving this introduction to all. Then we will go on to see how we reached to Moon from Earth. What are the different kind of things that we did to reach there? Then the most critical part, that is landing on Moon. That is very critical. This is where we failed in Chandrayaan 2. And then as the last part, the various operations that we did in Moon to explore the science and that of scientific interest. So this will be the last part of the topic, last part of today's presentation. So let us go. So we know that Moon is orbiting around Earth. So just play a simple animation, just see how it orbits. So you can see this arrow here. As the Moon is revolving around Earth, it is rotating on its own axis also. So, and one more fact you can see here, that when Moon completed one set of revolution around Earth, it completed one spinning on its own axis also. That means the time period of revolution of Moon around the Earth is equal to the time period of spinning of Moon on its own axis. Now, as a result of this, what happens? Always one side of the Moon will be facing the Earth. From Earth, we will not see the other side of the Moon. So this is how it happens. So once again, I'll play that video for you. You can now clearly understand the Moon spinning on its own axis while revolving around the Earth. And it completes exactly one spinning when it completes one revolution. So this particular fact, it is not a coincidence. It is not a coincidence, but this is due to a physical phenomenon called tidal locking. So we say that Moon is tidally locked to Earth. We will not go to the details of the tidal locking. If required, I will share you a link of the video in the end of the talk to understand tidal locking in the simple terms. But now we'll go forward by carrying this information that Moon is revolving around the Earth. At the same time, Moon is rotating on its own axis also, and Moon always present its one face towards the Earth. Now, what does it mean? So it means that now let us look about the lighting on the Moon. Now we have Sun here and Earth here, and I have shown here the position of Moon at different places, different phases of its orbit. Now, Sun is always lighting up one half of Earth and one half of Moon. So you can see here, see here, see here, and see here. It is always lighting up one half of the Moon. But as Moon is revolving and rotating around its own axis, so the different parts of the Moon get lighted up. It's just like Earth. So that means in Moon also we will have this day and night, because Moon is also spinning on its own axis. So assume that we are staying at this dot that I represented here. Now what happens? Right now, this dot is receiving sunlight from the Sun, which is on this part. Sun is lighting it from this side. Now what happens? As the Moon revolves around the Earth, it goes like this, and now we stop receiving sunlight. So that means if we are on Moon, this would be our sunset. Then from there onwards, it will be night for the Moon. For anybody in the Moon, it will be night. Now again, we get to the sunrise. We start to seeing Sun, and there is a sunrise on the Moon. Again, for the next 14 days, we get Sun. So we can say that in Moon, we have the duration of the day as 14 Earth days. It starts here because the complete revolution of Moon takes around 28 days. That means half of that, one particular place in Moon will be lit by the Sun, and half of that, it will not be lit by the Sun. So for the half of the time of 28 days, that is 14 days, it will be day in the Moon, and for next 14 days, it will be the night. So this 14 days duration, we call as one lunar day. Fine. Now let's go to the next slide. Now, we know that Earth has a North Pole, South Pole, and it is rotating and spinning around that particular axis called pole. Moon also has a similar axis in which it is rotating. That means Moon also has a North Pole. Moon also has a north and moon also has a south, because it is like Earth just spinning on its own axis. Now, the average distance between the Earth and the moon is 3,84,400 kilometers. This is just the average distance. When moon is orbiting around the Earth, this distance changes. The actual orbit of the moon around the Earth is not a purely circular one. It is slightly elliptical. So this distance varies. And not only that, during the course of an year also, the distance between the Earth and moon varies. So this is just some basics about the Earth-Moon rotation system. Now, do you know another interesting fact, that if you are in northern hemisphere, that is in Earth, if we are above the equator, we will be standing like this on the surface of Earth. And when you look to moon from anywhere on the northern hemisphere, the top part will be this and the bottom part will be this. So we will see the moon like this, where this particular crater will be down. Okay, this particular crater is a huge crater that we can identify the location in the moon, or these black spots. Now, what happens if we are on southern hemisphere, that is below the equatorial plane of the Earth? Now we will be standing like this, heads down. So our top part will be this. Our top part will be the south of the moon, and our bottom will be this part. That means our top will be this. That means we will see the moon inverted, and this particular crater will be on this part. So this is how, if you are in northern hemisphere, you see a moon like this, and if you're in southern hemisphere, you see the moon like this. And India is on the northern part. That means we always see moon like this. Now, so we know that we have a north, we have a south, and we all know that we Indians have landed near the south pole of the moon, and that is this spot that we see. We actually landed here. This is the place where we landed, near the south pole of the moon. Now, how do we define this point? This is just a vague point. How do we define this point in terms of numbers? So let us see. Now, what we do is, this is a scientific method that we use to define in any planet or any particular point in a planet, including Earth. So first we define a line called equator, equatorial axis. It is like this. It is a plane. Now we define another line called prime meridian. So in the case of this moon, we have selected a line which is closest to the Earth, because we all know that moon is always presenting its one face to Earth. So whenever we look from Earth, we can easily identify this line. So this line is defined as the prime meridian of the Earth, moon. Now, what we do? Now here we see what we do is, we just draw some lines like this, which are at 10 degree apart. So this line is 10 degree apart, and this line is 10 degree apart, this line is 10 degree apart, like that. And these are called latitudes. For Earth also we do that. These are called lines of latitude. And towards the east and towards the west, we draw another set of lines which are also 10 degree apart, and these lines we call lines of longitude. Now, we landed at a place which can be marked by 69 degree to the south of equator and 32 degree to the east of prime meridian. That means 69 degree. So we have to count 10, 20, 30, 40, 50, 60. And 69 comes somewhere around here. And now to the east from the prime meridian, 32 degree. 10, 20, 30. So this is the spot where we landed. And remember, if we use a telescope from Earth, we will be able to see this face of the moon as I have presented here. And we will be able to identify this big crater. And if you ever happen to identify this big crater on the moon, seen through a telescope or via a zoomed lens, just make this spot. This is where our lander Vikram is available as of now. So now in a three-dimensional plane, in a 3D, where do our landing site lie? It is here. This is the place where our landing. This is the place where our Vikram lies now. And this was the alternate plan that we had in case if this landing failed, we would have gone to this. This was the secondary landing site that we had identified. So now, did we just go like to moon without making any proper homework and all? It's not like that. In fact, we have the orbiter of Chandrayaan 2 available orbiting the moon. So we mapped the entire surface of the moon. Currently, we have the entire lunar surface map with a resolution of 25 centimeter. That means it comes around this much. That means if there is an object of this length on the moon, it will represent 1 pixel in the photograph that we take from Chandrayaan lander, or we will be able to identify anything longer than this on the moon surface. So we continuously scanned the south pole of the moon and we identified one area in the south pole which is relatively free of any larger craters. Okay, so this is the particular area that we have identified. I have just zoomed this area, and this particular area is of a size of 4 kilometer in length and 2.4 kilometer in width. And what did we do further? We identified this area and we made a hazard map for this. Like this, you can see this is a particular hazard map that we have made for this. So you can see here we have spotted something in red. So this spot corresponds to this and this spot corresponds to this. These are all small craters and boulders available in the lunar surface. So we have mapped this particular area and we have converted into a hazard map identifying the safe areas for landing of our craft, of our lander. And this particular information is stored on board onto Chandrayaan 3. So Chandrayaan 3 has this information. So based on this information, it is supposed to find out the exact location of landing on the lunar surface. Is that fine? Okay. Now, the next question is, now we have finalized the south pole. Anyway, Vasant has introduced it in a very good manner that why we have decided to go to south pole. Now I try to give some technical reasoning for it. Okay. So now we have light of sun coming from here in this direction. Now, as you know, this is the equatorial plane of the moon, and this is the axis along which it is spinning. So now the light is falling straight ahead on the equatorial plane or over the head on the equatorial regions. So while the moon is spinning, all the craters, the inside part of the craters in the equatorial region also will get lit up. Now, what happens to a pole? In a pole, light would be coming in this direction only because sun is always here. And assume that we have a crater like this, a big crater. Assume that we have a big crater in south like this. Now, this light will be coming in a tangential direction to this crater. That means some region of the craters will be always in shadow while moon is spinning on its own axis. And such one crater is what we see here. That means in the poles, we will have some region in the moon surface which would not have received any light from the time moon evolved. That means moon and earth evolved almost around the same time. That means we are getting an opportunity to look into some region which has not received any light or any energy from earth and moon evolved. That means there could be some secrets of the evolution still available there. That is why we are interested in South Pole. And since some of the regions are in permanent shadows, that means there could be a presence of water ice also available there because the temperature there is less than around minus 200 degrees. And you know that it would be ice at the temperature. And there would be some materials which are still pristine in its form, from the time Earth and Moon evolved. So these are the basic reasons why we have selected the polar region of the Moon for our excavation. Okay, so that is the end of the first part of the talk about the Earth-Moon system. Now, if you have any questions on this part, I think we can take it.
Yes, sir. Wonderful explanation. And a lot of kids cannot resist, their questions they've been continuously asking. Although we were able to answer a few of them, I will curate few of the questions from the participants here. So there is a question from Manya Samant, where he asked, why I have heard that Vikram will only work for 2 weeks. Is it true?
Vikram may work for more days, but we have ensured that it will work for 2 weeks. The reason is that, now, I have already explained to you that we have 14 days on the moon, and then the next 14 days will be night. Now, what happens during the night? The temperature of the surface of the moon will go down as low as minus 200 degrees centigrade. Now, this time, we have not tested that all systems work at that temperature. Or if you want to design for that temperature, we need to put some heaters and all for heating certain elements during that period continuously to keep certain equipments warm and not to go below the required temperature for that particular equipment. Say we have a camera or an instrument which has some electronic parts like resistance, capacitance, or some circuit welding or something like that. That particular element will have a temperature limit. So we have to keep that particular element above a certain temperature. It is possible. The only point is that for this mission, we have not designed it that way. So we have ensured that it will work for the complete 14 days of the lunar day. Now, after the next 14 days of night, we will try switching it on. Sometime it may work, but we cannot guarantee that. That's all.
Okay, got it, got it. Even I got good insights for that question. And there's also a question from Prasanna Kumar, who is watching the session in YouTube. So he said that there is a rumor of living organism found in moon. Is it true? I know it's a difficult question, but he's quite reluctant about knowing an answer for that.
Currently, we don't have any positive confirmation of such an information, so it may be still a rumor. But such kind of things, will come after a wide study. It's not a question that we can answer on a go.
Right.
We have got tons of data. We have got tons of the data from the moon, and it will take a lot of time for proper analysis of that. So at this point of time, we cannot comment on anything like that. So let us wait a bit more to get such answers.
Right. And there's also a question from Ridhima. I'm sure you would be addressing this in the coming slides itself. Maybe you can just give a glimpse. So Ridhima's question was, Chandrayaan 3 was launched on 14 July, but it took 40 days. That's almost more than 2 lunar days. So why was it very hard for us to land on moon while rotating? That's
anyway, you can see the heading of the slide. It is reaching the moon from Earth. So I'm going to address exactly the same thing in the coming slides.
Okay.
So wait for that so that I will get the help of the graphics to explain it in a much better way.
Okay, so Ridhima, you can actually, Sir is going to explain you with more videos and photographs. And I think, we are good to go for the next session, sir.
Okay, fine. Thank you. So let's go. So let's think about reaching the moon from Earth. So lander Vikram is ready to be transported from Earth to moon. And this is how he looks like. He has a lot of elements with him, which he has some, you can see some nozzles through which the fuel and oxidizer can be burned and some upward force can be generated. And there are a lot of instruments here and there supporting the communication and some cameras and all. So this is about the lander Vikram, and so lander Vikram is ready to go to moon. Now, next question is how to go. So this is our launch pad, Sriharikota, what we see in the left side, and we are intending to go from this part of the Earth to this part of the moon. So how to go is the biggest question that we need to address. So what is the problem? Problem is gravity. Now in Earth, we are under gravity, and we cannot simply go up as we wish. And we need to go to moon, the gravity. But the problem may not be that critical because the moon is also under the influence of gravity of Earth because moon is orbiting around the Earth. That is because moon is attracted towards the Earth by its own gravity. So actually what we need to do is we need to change or we need to transport lander from one gravity body to the other gravity body. And the second gravity body moon is still under the influence of the Earth. So, and we know that moon is orbiting the Earth too. That means we can also try for a similar thing. Let us try to orbit around the Earth and reach the moon. Now, you would have seen in some fiction movies and all, get into one rocket and then fire the rocket continuously and to go to moon like this in a zigzag manner as we see as we ride a car in a road and all. So now that is also possible. That's not impossible. But what is the problem with it? The problem with it is that you need to have that much fuel. You need to spend that much fuel if you want to go that way directly in full control to the moon. If you need to carry that much fuel, that means the amount of fuel that you need to carry in our lander would be high. That eventually means that we have to carry that extra weight in the lander, which is not called for. And our rockets will not be capable to carry that much extra weight also. So what we have to look at is, we have to look for a way to reach moon by spending the minimum possible fuel and with the rocket available with us. So the solution for the problem of gravity is to go into an orbit using a rocket. That is what we can do. Now, when we say about going into an orbit in a rocket, I would like to spend a little bit of time here just to explain how things remain in an orbit. So let us say this is the Earth, and we are going to the top of the Earth, top of a hill in an Earth, and throwing ball in a horizontal direction. If you throw in a smaller velocity in this direction, you can see the ball will come and drop here at the point A. If you throw it in a slightly higher velocity, it will go and it will fall at the point B. Now, what if we throw with a velocity such that it always tries to fall towards the Earth, but it never reaches the surface of the Earth? Gravity is always acting on it and it is curving towards Earth, but because of the velocity it possesses, it is not able to touch the surface of the Earth. So at sea, if you see, it continuously remains in the space. And this is what we call as in orbit. It is continuously falling towards the Earth, but it is not able to reach the Earth. Now, for each altitude, there is a particular velocity with which you need to throw to put it into an orbit. And this kind of an orbit, which is of purely in a circular nature, is called a circular orbit. Now, another interesting question: what happens if we throw with a velocity which is slightly higher at this point than required to make a circular orbit? So it goes to an orbit like this, which we call as an elliptical orbit, because the distance to this point of the orbit is lesser compared to the distance in the other point of the orbit. Distance to this point is higher. So we call it as an elliptical orbit. If you throw with a much higher velocity, more than what we call as escape velocity, which is 11.2 kilometer per second, it will go out of our gravitational effect. So this is how things remain in orbit. Now we are going to put something into orbit. Now we look to the most powerful rocket that we have. So this is where we get some limitation that the most powerful rocket that we have has a capability of taking around 4,000 kg to an orbit of 180 kilometer and with a speed of 10.3 kilometer per second. If we had a rocket of much higher capability, this number of days could have been reduced a little bit lesser. So there is one answer to it. If you see the mission of Lunar 25, which Russians launched, it did not take 40 days to reach moon. It took only hardly some 4 or 5 days to reach the moon. That is because simply that their rocket was more powerful than that. We have to agree that. But the most efficient way would be what we do, because we use lesser mass of fuel to reach the moon, even though it takes more number of days. So we look towards the most powerful rocket of India, that is LVM3 M4, and we ask him how he can help. So he says, I can take 3,900 kg to 179 kilometer altitude and give you a speed of sub 10.3 kilometer per second. Okay, that's fine. We accept it. Now that particular orbit, when we take the Chandrayaan to altitude of 179 kilometer and put it like this, it is actually an elliptical orbit. Elliptical orbit with the lowest height, which in technical terms we call as perigee, as 170 kilometer, and the largest height, which in technical terms we call as apogee, as 36,500 kilometers. But with this orbit, we are not going to reach anywhere near the moon, because the moon is 384,000 kilometers away. And we are now talking about only 36,500 kilometers. So we need to go 10 times higher, or we need to make this such a point called apogee point, not just 36,500, but 384,000. How to do that? So the speed that we are providing here is not enough to reach the moon. Now, that means we need some more push to reach the moon, even after taking the help of this giant rocket. So what to do that? How to do? So we decide to add something called a propulsion module below the lander. So the propulsion module will take care of taking the lander to the required orbit in the moon. So this is how the propulsion module looks like. So this is the lander, what we see in the top, and this is the propulsion module. So we add a propulsion module just below the lander. So this is a photograph of the propulsion module that actually went to the moon. So this is the lander and this is the propulsion module. So we add a propulsion module to give that additional energy to the Chandrayaan to reach the moon. Now, so we have decided that we need to give some additional thrust. That is clear, that is understood, the requirement is understood, because our launch vehicle could put it only into an orbit of 170 kilometer to 36,500 kilometers. So, but the moon is at this location at 3,69,000 kilometers. I will clarify this particular figure, 3,69,000 kilometers later. So, we need to reach at least a 3,69,000 kilometers as the apogee of the orbit. Now, so it is clear that we need to give additional energy or additional burning of the engine, which is there, the propulsion module. Now, where should I burn? Now, if I burn here, what will happen? Is it okay? If I burn here, actually I am adding the speed or velocity in this direction. It is the direction is just tangential to this point. That is the direction in which I am adding the velocity. If I add velocity here, it will not raise this point. Instead of that, it will raise only the opposite point. The opposite point also will become 36,500 kilometers. But that is not our requirement. Our requirement is that this point should reach 3,69,000 kilometers. So for that, let's try another combination. What if I burn here? It looks like if I am burning here, burning the engine here, I am giving additional thrust in this direction, additional force in this direction, whereby I am increasing the velocity in this direction. So this point I am not changing, because this velocity is always tangential to this path. So this path of the rocket, so this path of the satellite is not compromised, but additional velocity is added. It is as if our rocket is coming here and throwing it with a much higher velocity at the same point. So what happens? Yes, if we give that required velocity at this point, we will be able to reach moon like this. So this is the trick that we play. Here, we do not go out of the gravitational influence of Earth. We are just playing with orbits. So we go to one orbit of Earth, and that orbit we keep on racing continuously till we reach the still in the orbit, but on the path of the moon. This is the trick that we are playing. So this way, we are transferring our spacecraft from the gravitational orbit around the Earth to a location where moon is there. So the final orbit that we achieved in the case of this spacecraft or the Chandrayaan was 288. That will be the distance here, and the apogee point or the farthest point on this orbit will be 369,000 kilometers. And why we had to go to the multiple orbit? It is because we know that earlier I told that we have to always fire in a tangential direction. Now, when this is in the orbit, the time for which the satellite remains in the tangential direction will be less because it will be orbiting like this. So we need multiple firings like this to ensure that we are giving velocity only in the tangential direction so that the other part of the orbit will get raised. This particular operation is technically called as orbit raise. This is how all the orbits of the satellites are raised once it is put into one particular orbit by a rocket. So now from Earth we started. After certain orbits around the Earth, now we have reached at a point where moon would be coming at that distance. Now, what we do when moon comes there, now our craft or our lander is traveling at a much higher speed if we compare the speed required to enter into the moon's orbit. Because I'll clarify this a little bit more. The gravity of the moon is 1/6 of the gravity of Earth. It is much less. So, if you are thinking to put one particular satellite in the orbit of moon, it will require much lesser speed only. Now, as part of this orbital maneuver, when we reached at this point, the velocity available for the craft was much higher than the velocity it needed to enter into the moon's orbit, or the velocity it needed to fall towards the moon. When we say we are in the moon's orbit, it is nothing but falling towards the moon. If you do not reduce velocity here, it will just take a flyby and it will miss the moon's orbit and it will just go like this. So at this point, we just make our craft, we just rotate our craft 180 degrees so that our thruster becomes on the back side and we thrust it like this. So we are applying a force on the craft like this. We reduce the velocity, we reduce the speed, and we match it to the speed such that it will get caught into an elliptical orbit around the moon like this first. Then we do again orbit reduction in the moon surface step by step. Then finally we reach into a particular orbit from where we can attempt a landing on the moon. This is how we go in the orbit. So let us see how it caught up with the moon's orbit. This is how it caught up with the moon's orbit. And then the orbit in the moon was reduced step by step. And finally, it got into a closed orbit from which we can attempt for soft landing. So as a whole, if you see, when we started, the moon was here. So moon was traveling like this and moon continued traveling like this. And we reached around the moon's orbit when moon reached here and we got moon into the orbit. So we had to plan this in advance. For this earthbound orbit racing, we needed around 22 days. So if we had planned for a particular day to catch up with the moon, we had to launch 22 days before that particular day. This is for catching up with the moon's orbit. So now how do we decide then based on this the date of the launch, time of the launch, and related aspects? Let us have a quick look into it. Now, it would be better if we catch the moon when it is closest to Earth. I already mentioned that the orbit of moon is slightly elliptical. So the distance between Earth and moon varies over the orbit of the moon. And not only that, this is the nominal values, like the shortest distance 362,000 kilometers and the largest distance 4 lakh kilometers. But these two, if you see the variation of this particular distance over the months in a year, in January, we have this distance as the shortest one, then in August also. So January and August are two possible periods where we could have launched Chandrayaan. And we launched on August. The reason for this is because now Earth is not the only planet which is exerting its force on the moon. As the Earth-Moon system is revolving around the sun, There are a lot of other planets also which are at a much higher distance, agreed, but still there are some masses like Jupiter, Venus, Mars, etc., which will also have some effect on the moon, due to which the orbit of the moon will be slightly increased, decreased, and all. But if you see the data, it is on January and on August that we get closest to the moon. So we decided a date called date of August 5th to get into the orbit of the moon. So at August 5th, if sun is here, the moon was here. Now, if you want to catch up the moon, now there is one particular thing that we have to take care, that the orientation of the orbit had to be like this. While launching from Earth itself, we cannot make an orbit of orientation like this and think to catch to a moon which is going to come here on that particular day. So this particular orientation of the orbit around the moon is very important when you're launching, when you're aiming to catch up moon, which is at this particular location on August 5th. So now the date of the launch we fixed, because we know that we need around 22 days to reach the moon through the orbital maneuvers that we are going to do around Earth. So we subtract around 22 days from August 5th, we get the launch date of July 14th. Now, to launch at what time of the day? Let us try to understand. We know that the Earth is spinning on its own axis like this. So any point of Earth due to spin, if you see any equatorial point of Earth like this or like this, they are all moving with a velocity like this. And do you know what is this velocity at the equatorial point due to the spinning of Earth? It is around 464 meter per second. 464 meter per second means it is 0.4 kilometer per second. Now, earlier we saw that our LVM-3 had a capacity of throwing the satellite into an orbit with a velocity of 10.3 kilometer per second only. So, out of this 0.5 kilometer per second is already available here. So, we should make use of that. So, we should be launching in this direction only because it is rotating like this. So, we need to take advantage of the fact that this particular point in an equator is also moving with a velocity like this. Now, we know that we need to get an orbit like this. There is absolutely no doubt on that because then only we will be able to catch up the moon. Then, can we launch when our India is here? No, because then we will be getting an orbit like this only. That is not useful for us. So we should launch when our India is here. The sun is here, so this is the mid-noon, that is around 12 o'clock. So if you want to launch it around here, like this, the rocket should go like this and it should launch here. Then what should be the time? You can already imagine, this is 12 o'clock and this is the sunset, so it will be around 2:35 p.m. So this is when we launched it. So this is how we fix the date and the time of the launch. So we launched it like this. Now we know that any point on the moon's surface will be having day and night. Now we launched it while it was here. The moon was here, while some parts of the moon were lit up by the sun. Now we have identified a point for landing in the moon. Now we know that the sunlight on that part is very important for carrying out our activities. So there is no point in landing to that site if it is immediately going to be darker there. So we need to land at that point when it is morning there. This is another important fact. And this is our landing point. And on September 23rd, it is morning there, actually September 22nd. So we decided to land on the moon on September 23rd. So this is the whole story of the mission planning behind this. And we are all finalized and we are ready to land. And what happens? Now we have entered into the moon's orbit. Now the propulsion module has done its part. And now we separate the propulsion module from the lander. Now the propulsion module is separate, lander is separate. Propulsion module will continue to remain in the orbit of the moon and lander will take its course for landing in the moon. So that's it. So when it was separated from the propulsion module, lander reached into an orbit of 25 kilometer into 134 kilometers. So 25 kilometer was the closest distance to the moon and 134 kilometer was the farthest distance from the moon. So that's the end of the second part. Now we'll go into the climax for the final 30 minutes of the landing.
Um, yeah, hello, sir. This was very useful, and I couldn't resist asking you questions because children are behind me. So would like to ask you a few questions. I hope that is fine.
Yes.
Okay, great. So there was a specific question that was asked by a lot of kids, like Pranav, Vidishri, Anish, Aradhya Agarwal. So they asked this question: Why did Chandrayaan 2 fail? If you can throw some light on it.
That particular point, I will answer in the end of the talk because still these aspects related to that is yet to be covered.
Okay, great. And there is another question from Maushmi Das, like how do you accurately measure the time of landing as the rover is quite far away? And also what happens to the parts of the rocket that fall off?
We plan the launch of the rocket. This is not applicable only for the Chandrayaan launch, for any launch. That question is valid. So
Right.
the particular time of the launch, I think it is based on the orientation of the orbit that we need to get around the Earth, which I think I have explained. Because if you want to get a correct orientation, because Earth is spinning.
Mhm.
If we look at a point with respect to space,
Mhm.
maybe a star, sun, since the Earth is spinning, it comes to a certain position with respect to the stars only at a certain time.
Mhm.
If you want to get a particular orientation towards a particular body, celestial body, we need to fix the time of the launch because we are launching only from a particular point in India called Sriharikota. So we need to identify a particular time when the Sriharikota is around that time. That is how we fix the time of the launch. Okay. Now coming to the second question. What is the question was the second question?
What happened to the parts of the rocket that
Fine.
fall off?
Now we know that a rocket is made of multiple parts, and after the functioning of the first stage, that stage gets separated, and second stage gets separated, and all. Have you ever thought why we have kept the launch pad near Sriharikota? Because it is so close to sea. So we are launching towards the sea. So our rocket is always flying on the top of the sea, through the sea. So these parts are actually now falling into the sea. That is what happens. And we, in fact, before each launch, study in detail the possible areas where the separated parts would see. And we, in that way, ensure the safety and then only we launch. They're actually falling into the sea.
Okay, got it. And there's also one question that, how is it possible for us to control the rover from thousands of kilometers away?
That question also I will answer later when we come to that
Okay,
one.
okay,
I'll
okay,
answer.
great.
Keep on these
Okay.
questions, and if I'm not answering you, please remind me. Okay.
Yeah, definitely, sir. Yeah, I think, we are good to go. I would, try to answer the other questions and we'll also curate more questions towards the end.
Yeah,
Yeah,
fine.
please continue, sir. Yeah.
Yeah, fine. So now we are going to the climax or the point of no return. Why I say this is the point of no return? So far, the lander is in orbit. If we don't do anything, it will continue to be there. And if any orbit correction or something is required, it is possible for us to do. Now we are going to attempt to land on the moon. And once we start that operation, then there is no going back to orbit, nothing. We have to land. Either we have to land, we will try our level best to land softly. And this time we have ensured almost that we would land softly, or we will crash on them. So there is no point of return. This is the point of no return. Now, so far, the lander was aided by a lot of commands from Earth. Lander has its own antennas available at this part of the lander, through which it is communicating to orbiter and to some big antennas we have kept in Earth and all. So we are communicating to the lander through by sending signals through those antennas and all, through the transmitters and all, and receiving back the signal through the antennas and all. So we are communicating like this. But now from this point to the next 30 minutes, now lander has to make a lot of quick decisions based on where it is and what distance from moon it is and all. While it is in orbit, it is easy for us to understand the altitude and other positions of the lander. But still we do not know how far it is from the moon surface, because moon surface is not a planar one. It is a spherical one. And even within that, there are boulders, craters, there are altitude variations and all. For example, if we see the point that we landed is 522 meters above the mean lunar surface. So it's not about the mean lunar surface that we need. We need information or how far our lander is about the particular point that we need to land. So we have given a lot of sensors and eyes to the lander. So far, those sensors and eyes were not useful, but from this point of time, lander needs to open its eyes and understand its position and where it has reached and to take a lot of quick decisions. At this point, we load an automatic landing sequence program into the computer of the lander. And from there onwards, it has to take care of that, make decisions based on that, no intervention possible from Earth, because a command going from Earth to Moon will take more than 1 second, because the distance is 384,000 kilometers, and light can travel only speed of 3 lakh kilometers per second. So even if travels at the speed of the light, the information travels at the speed of the light, it will take more than 1 second. So there is no question of a communication from Earth. Lander has to make its own decisions. Okay. So let us see how it goes. Now, this is the 4 phases now we have to go in. I will not dwell much on this slide. I will explain each of the phases in detail in the coming slides. So first we are starting from here. We will orient the lander like this, and we will start firing the engines of the lander. So it will come from 30 kilometer to some 7.4 kilometer. That particular phase we call as rough braking phase, because we are applying the highest possible thrust to reduce the velocity aiming at a landing site. Then the next phase is called attitude hold phase, and then fine braking phase and terminal descent phase. Let us see what happens through this phase. So we have started rough braking phase. We are caught up with an altitude of 30 kilometers, which is part of the orbit in which lander was already in. At the time, lander had a velocity of 1.68 kilometers per second. And we fired the engines like this. So the lander velocity reduced. And you know, any orbital body, when its velocity reduces, starts falling towards the moon or Earth, whatever it is, in a more steeper path. And that is what happens here. So when velocity reduces, it starts falling in a more steeper path. And the whole time that we took for that operation was 690 seconds. And the horizontal distance that we covered during that operation was 713 kilometers. So we reached from an altitude of 30 kilometers to 7.4 kilometers by firing all these small engines or pushing the lander up or reducing its velocity. So we reached 7.4 kilometers. So we have completed now the rough braking phase. Now next is, there is a phase called attitude control phase, attitude hold phase, or a camera coast phase. This phase is only for 10 seconds. This is where we faltered in the case of Chandrayaan 2. So listen carefully. I will explain. Now, this phase is required because, as the name suggests, it is a camera coast phase. So we are keeping the spacecraft in a particular angle, in a particular inclination, orientation. We will not allow to change this orientation from the start of the coasting phase to the end of the coasting phase. This is required because we have already identified a piece of land in moon for landing. And that information is already fed into the computer in the lander. We have made a hazard map. Now, during this point of time, the camera is looking for that surface and confirming that surface which is available in the moon and comparing it with the hazard map which is already available inside the lander. So it is locking that phase of landing. Now, here we know that we need to keep this altitude in a particular orientation. Sorry, not altitude, attitude in a particular. There is a difference between altitude and attitude. In many media, this particular phase is referred as altitude hold phase. It is not actually altitude hold phase. It is attitude hold phase. Attitude means it's about the orientation of the spacecraft. Okay. So this orientation we are holding like this so that cameras will be always aligned in one particular direction. Now here what happened was that this system will be continuously measuring its height, etc., from different eyes or cameras and sensors in the lander. Now we get a feedback of that also. Sometimes things may not be going as we planned. So the attitude is maintained okay, but the speed may not be reduced as we planned. Now, here in this particular mission, what we do is we look at the speed in which it is going, even though attitude is maintained. The speed, if it goes higher or lower, we start controlling it then and there itself by adjusting the thrust. But in Chandrayaan 2, we kept this particular process towards the end of this point. So throughout this point, we did not control the acceleration or control the speed of the aircraft because we were aiming only at this. So this is not only due to that, the engines were slightly of the higher thrust in Chandrayaan 2. So that was also due to one particular issue that we faced with one of the valves, which we used to operate through engine. So it gave some higher thrust, and this, along with this particular logic implementation, when it reached at this point, since the thrust was higher at this point, thrust was higher, the speed got to a very low value in Chandrayaan 2. Then what should happen? So when the speed is very low, now we cannot reach here because we need some speed to still cover the distance. So in Chandrayaan 2, what happens when we reached here itself, because the thrust was high and we did not attempt to control it during this trip, and we were thinking of controlling it beyond this, that could also have worked if the other valve issue did not happen. So it was a multiple problems coming and creating some issues for the software and hardware, etc. So at this point, it had only very low velocity compared to what it should have been. So the craft still wanted to go and land this point where it was intended to land, but here it did not have velocity, so it could not go here. So it just went somewhere here and crashed into the moon. So the vertical velocity was gained, but the horizontal velocity was killed. This is what happened in Chandrayaan 2. So it is a kind of a unsatisfactory hardware performance plus some algorithmic errors and all together, and there are certain other artificial limit of correcting the rate limited to some 10 degree per second. If that was still higher, then still it would have landed. And then the whole crux of the problem is that that particular mission was a success-oriented approach while designing the software, designing the hardware, and we did not consider attending a multiple failure scenario. One failure for each system we would have considered, but a multiple failure scenario, how to still land safely, that particular aspect was not 100% addressed. It was addressed to a limit, but not to 100%. But this time, we have tried to attempt almost all those problems, and we had added multiple possible options for landing. If this happens, if Y happens, if X happens, and all. And so we were almost confident of a safe landing. So our camera course phase is completed. Now we have next is a fine braking phase. So in fine braking phase, so during this phase, before going to the next slide, so it was comparing with this image available on board the camera with the actual surface of the moon. Next comes the fine braking phase. In this fine braking phase, when we start the phase, we are at an altitude of 6.8 kilometers, and we have the velocity of 336 meters per second. And in the end of this phase, our velocity would be 0 meter per second, 0 meter per second. That means we would be literally hovering on the top of the surface of the moon on the end of this phase. So during this phase, we will be making use of almost all the sensors that our lander has to consider to find out the altitude and the velocity and the other parameters. And we finally get to this phase called fine braking phase. At the end of the phase, we are at a particular altitude of 0.8 kilometer and zero velocity. Zero velocity means we are hovering there. We are just standing still there by employing our thrusters. We are just providing the required upward force, which will cancel the gravity. So we are staying there. Upward force equal to gravity. So we are staying there. And during this time, we are using our sensors are continuously working. LDV, laser Doppler velocity meter. This particular sensor, we did not have the sensor in Chandrayaan 2, laser Doppler velocity meter, which is a critical sensor which will give you the absolute velocity of the body with respect to a surface. And we actually tried to procure this from abroad last time for Chandrayaan 2, but nobody gave us. But then later, we ISRO ourselves developed it, and we have successfully used in this mission. And this sensor is one sensor which we can rely upon and which we relied upon for the successful mission. And this is CARA K-band. It's K-band, it's a frequency band. I will not tell much on this. And this is RS stands for radar altimeter. So using a radar technology, we will be getting the height of an object above a surface. And LASA is again laser-based altimeter. It is again another altimeter which we use for cross-checking of the altitude which we get using CARA and LASA. And LHV is a lander a horizontal velocity camera. Through camera, you'll try to find out the horizontal velocity of lander. So for all the measurements, we have redundancy. We have more than one equipment to give the value. So we'll compare the values that we receive with instruments. That's how we go on. And then we had a hovering at 800 meter. Then after hovering for 12 seconds of 800 meter, we closely watched the landing site. And because we had only an image of 25 centimeter resolution earlier. Now we are much close. So we can see the landings, particular area in which we are going to land more closely. We have identified a 4 into 2.4 kilometer strip. That is fine. Now, where exactly this lander is going to land, we are trying to identify by hovering. And then we again come to one more phase called this terminal. This entire phase is called terminal descent phase. Terminal descent phase, where we will be coming straight away down. So we now come to 150 meter. Again, we have a 22-second hovering while we are just analyzing the surface below, whether everything is okay or is there any crater, small crater, which we could not identify earlier, but now it is there, so that landing would be a problem and all. And we, in fact, identified one small crater, so we just moved to 150 meter aside and we landed in another area. This is how we landed. And for that, what helped us is something called LHDAC, nothing but Lander Hazard Detection and Avoidance Camera. It is a camera which we have programmed to see a surface and to find out hazards in a real-time manner. So we looked through the camera, we found some hazards. So this is already programmed that if we find a hazard here, we go to 150 meter away and land at some other place, which is safe after having a look at that place. And this is how we landed. So we successfully landed. And here, I'll just show you a video of how the visuals from the camera would have looked like. But this is this is an image which we converted into video. So quality is slightly lesser, but lander would have had these images at a much higher quality to evaluate. But this is what we received at Earth during that process. So it is going down. So we are seeing that through the camera, the lunar surface, changing lunar surface, we see that it is now this fine breaking phase is going to be over. Now we can see after some time, if hovering, we can see where the image still holds. So you can see that image was still holding still. So you can see again, I will play it. You can see that image is holding good. That means there is a hovering phase. And after hovering, again, it started coming down. And then its second hovering, then it decided that it had to go a little bit far away for landing. So it went a little bit far away and it landed. So the final plume that we see is that while landing, now we are our rockets, the small engines on the lander is still functioning. So these plumes will go and hit the lunar surface. And when it hits the lunar surface, what happens is the dust of the lunar surface or the very fine powder in the lunar surface called rigor, it will form a dust. So that is what we see here. And this is how we landed. So we finally landed on the lunar surface successfully. And our lander pad touched the surface successfully. That's how we made the lunar landing. So Vikram, the lander, is now over the moon. The moon says, "Good morning, Vikram." So that is the end of the third part. I think I have addressed that point. Vasant, any more questions?
Yes, I think now we had a detailed explanation for the same question which kids have asked. Yes, sir. Yeah. Yes, sir. And I'll quickly curate some of the questions which students have asked. Or would you like to say something, sir?
Yeah.
Okay, great. So there's one question from Smriti who asked, I think you explained here, but if you can just, quickly brief it, that would be great. So how did Chandrayaan go to the moon while gravity of Earth is, stopping it?
Yeah, actually, we did not escape from the gravity of Earth. The answer for that is we did not escape from the gravity of Earth.
Right.
You see, moon is still under the gravity of Earth. That is why it is revolving around the Earth. If you measure the gravity of Earth at the moon, it will be quite a good value. It's not zero because moon is still attracted by the Earth. So the trick that we played here is using a rocket, we went into the orbit around the Earth. And in the orbit around the Earth, we have not escaped from the gravity, but we are continuously falling towards the Earth. But because of the velocity we have, we are continuously escaping the Earth. Then this orbit, we continuously increase. to a point that we reached on the farthest point of the orbit. We found Moon. When we found Moon, what we did? We adjusted our speed such that our craft would enter into the orbit of the Moon. Still, what happens? The Moon and the orbiter is together revolving the Earth. Imagine, Moon is not something that is different from the Earth. The Moon and the Moon and our spacecraft is together revolving around the Earth. So we are not away from the gravity of the Earth. You can think of it like this. There is a sun, there is an Earth. Okay, Earth is under the gravity of the sun. And there is a Moon revolving around the Earth, which is not again away, which is not free from the gravity of the sun. But Moon is closer to the Earth. So the gravity of the Earth on the Moon is higher than the gravity of the sun on the Moon. So actually, it is the Earth-Moon system that is revolving around the sun in a global picture. Like that, here you just imagine that Earth is our sun. And the Moon is the body which is revolving around the Earth. Now we put one satellite to Moon. So Moon along with that spacecraft is revolving around the Earth. So both are still under the gravity. But the second body is more closer to Moon, so it is revolving around the Moon. And the Moon and the satellite together is revolving around the Earth. So we are still very much in the gravity of Earth.
Got it, sir. And there's one question from Sarah who asked, when does ISRO plan on sending a manned space mission to Moon?
Okay, that is a policy-based question. At this point, I do not wish to answer that. There are certain spokespersons identified in ISRO for answering such kind of timelines and all.
Okay.
Obviously, we are working on such a program called mission, for which some tests are going on.
Okay.
So we need to take extra care of all the mission scenarios that would happen on such a case, and we need to ensure that we do not end up in a failure. So tests are progressing. So that's all what I can say.
Got it, sir. And from Chandrayaan 1, how Chandrayaan 3 is different? That's a question from one of our students.
Chandrayaan 1, as question is about Chandrayaan 1, right? Not Chandrayaan 2.
Yes, Chandrayaan 1 and Chandrayaan 3.
Chandrayaan 1 we launched in 2008. Chandrayaan 1, the difference is that Chandrayaan 1 did not have a lander, but it had something called a moon impact probe, which the Chandrayaan 1 satellite got into the orbit of the moon. And from the orbit of the moon, we separated something called a moon impact probe into the lunar surface. And we took measurement from that probe while it entered into the moon and while it crashed onto the moon. It was designed to crash on the moon. So it is a probe which was just thrown to the lunar surface from the orbiter of Chandrayaan 1. That was how Chandrayaan 1 was designed. And Chandrayaan 2 had a lander. And in Chandrayaan 2, almost all the activities or almost all the mission phases were success except the landing. So still we have that orbiter functioning in Chandrayaan in a lunar orbit and sending us a lot of data. But the lander failed in landing softly. Because of that, we went for Chandrayaan 3, in which we have demonstrated the safe landing of the lander also.
Okay, got it. And there's also one interesting question from Aniket. So he has asked, does the satellite have some form of AI to help it land? Does any systems that uses AI, sir, at this point?
Yeah, definitely. Because in this particular slide, I think I've shown some these kind of things and all. Now, just imagine a pilot landing an aircraft. Pilot, while landing an aircraft, he takes a lot of decisions based on his sensory perception, what we see, and how he goes. If he is a little bit away from the runway, what does he do? He lifts the aircraft a little bit up to reach more to the runway, and when he reaches the runway, he put it down and goes like that. And now, but here we don't have a human being to do that. Do you know one thing? In Apollo 11 mission, when the Apollo 11 spacecraft was supposed to land on the moon, during the final phase of the landing, Neil Armstrong was sitting inside. So initially, the autonomous landing program was on. But this autonomous landing program was going to take them to a location more than 4 kilometers away than their intended landing site. Then, do you know what Neil Armstrong did? Neil Armstrong did. He disabled that automatic landing system and he took manual control. So he used a sensor to see where the lunar surface and where we want to land, and he controlled the thrusters with his hand, just like you control in a video game. So he controlled it and landed precisely. The human sitting there is always advantage. But now we don't have a human sitting there, but we have to take those decisions based on the sensors data that we get, based on the velocity that we get through sensors, and based on the altitude that we get from sensors and all, we have to take a decision. So this decision making is an AI program. We need we get some input. I am at this distance, I am going at this speed. Now I need to cover this distance. So whether I should reduce my speed, whether I should reduce my thrust, increase my thrust, this decisions and all have to be taken automatically. So there is definitely an AI sitting there. Okay, in the modern term, now we say AI is much far complicated, but all these computer programs using some sensory feedback are AI on it. So there is an intelligence going on there, which is replicating the human intelligence.
Okay, great. That's a very interesting insight. I'm sure kids would have enjoyed listening to that from you. And there's a question from Manas. He said, if the south pole of the moon doesn't receive sunlight during that time, how does the rover run? Like what
Did
source
not
of
actually,
energy?
yeah, that's a good question. We did not actually go to the exact south pole. As I explained, it is 32-degree away from the east. It's not exact south pole. It's slightly away. It's slightly away. So it would be like the sun would be there, but not over the head, always over the horizon. You'll see the sun just moving. If you're here, if your head is like this, sun will never come here. Sun will never come here, but sun will come here. If your head is in this direction, sun will never come here, but sun will be always here, and sun will move like this. So that's how it's different.
Okay, got it, sir. And there's one question from Vihan, and a lot of kids have asked this. Why is there a golden foil wrapped around the lander and the propulsion module?
It is not actually a golden foil. Only thing is the color is gold. Okay, this is actually something called a thermal protection system. So we are going through the space, and space is not compromising. Space, when it is under the sun, the temperature shoots up to more than 200 degrees centigrade on the plus side. And when it is not in the sun, when it is not receiving the sunlight, the temperature goes to minus 200. So it's going to this extreme temperature. So we need to shield the equipments kept inside against this scorching sun and the scorching cold. So we put some multi-layered insulation. It is called MLA, multi-layered insulation. And the outermost part of this multi-layered insulation is a plastic film called polyamide, which has that golden color. That is why we see it as a golden color. That is only color. It is not a golden foil, right? It is a part of multi-layered insulation, and the outermost layer of that multi-layered insulation is a plastic material, which has a golden color.
Okay, great. So many kids were confused with that, why is there a golden foil? Right. Great, sir. And there's also a few questions on the, current status of Chandrayaan 3, like, what's happening? Is there any
That's a
findings?
very, very interesting question that I will cover. My slide ends with that. Okay.
Okay.
That.
So, yeah, then maybe, we can continue with that, sir.
Okay. So, Vikram is over the moon. Back to the presentation. So now let us see what it did there. So it landed safely with a small velocity. Now we have to do a lot of scientific operations. So we're going to start a lot of scientific operations. And the first scientific operation is that we are going to run down the lander. In this video, first I will show animations, then we will see some visuals captured from the moon itself. Okay. So first, the one flap of the primary ramp is deployed like this, and then it gets locked here, and then the secondary ramp is deployed so that we actually get the length required for the ramp. It is managed like this: one primary ramp, secondary ramp, and lander is sitting there, still attached to the. Sorry, our rover is sitting there, still attached to the lander. Now the rover opens its solar panel. Solar panel is deployed so that it can get the required power from the sun. Now we have a communication starting from the lander to the rover to power on the rover. Rover has some small batteries and the power generation systems and all. It is a solar panel to charge the batteries and all. Now, so we get now the communication from the lander to the rover. And the rover always communicates back to the lander, and lander communicates back to the Earth. So the communication is always through the lander. Now we give command to the rover, hello, let's move forward. So it is moving down. It's moving down and it touches the surface of the moon. Now it traverses more surface. Now it plans its path based on the camera available in there. Now we will see certain onboard visuals. So this is the actual lunar surface that we see, and what we see here is the shade of the landing legs of the lander. Now we will see the ramp getting deployed to this region. So the ramp is getting deployed. So you can see the ramp has come out and the lander, sorry, the rover is sitting here. This is the solar panel of the rover, which will be deployed now. You can see that the solar panel is deployed now. Sorry. So the solar panel is deployed and the rover now is rolling down. And the rover rolls down and touches the surface of the moon. And rover continues its journey. You can see it has kept a trail of its wheel on the lunar surface. Lunar surface, as I told you earlier, it's powder. We will see looking like this, it is made of hard rocks. It's not like that. They're all powder. Because there is no wind there, there is no atmosphere there. Once it is, that powder comes into some shape, it will remain like that. So that's why we can see the trails or the marks of the rover wheels on the surface of the moon. And now we can see the rover will attempt to make a turn also. It is turning. So it can roll straight, it can turn, so it can go anywhere. So that is how the rover operated on the moon. Now, we have a lot of other payloads of scientific interest also in the Chandrayaan mission. I will just give an overview of this different payloads. I will not spend much time on this because this may not be of interest to many of you. So there is a Langmuir probe which is there to measure the ion or electron charge density on the surface. And there is a payload called Chastity, which is meant to measure the thermal properties of the lunar surface. We'll come to see the more details of this in the next slide. And there is something called ILSA, which is an instrument for lunar seismic activity, which will measure if any small quakes are there happening on surface of the moon. The surface of the moon will be always hit from asteroids and all due to the absence of atmosphere, unlike Earth. So there will be some seismic activity that may be happening on lunar surface due to this, that it will catch up. So these were the three payloads on the one more was there on the lander, which is a laser retroreflector. This was by NASA for accurately estimating the distance between the lander and the Earth. So then these were the 4 payloads that were available on the lander, and we had 2 payloads on the rover, out of which one was alpha particle X-ray spectrometer, which will send some alpha particles into the surface of the moon, which will excite some of the electrons in some of the materials there, and they will emit radiation back. We will analyze that radiation and will try to find out what those materials are based on the characteristics of that material, which we already know. That's how alpha particle X-ray spectrometer works. And this is another similar kind of instrument, laser-induced breakdown spectroscope. So these 2 instruments were there in the rover. And another interesting payload, SHADE, spectropolarimetry of habitable planet Earth. This was there in the propulsion module. We know that after separating from the lander, propulsion module continued its journey around the orbit of the moon. So it had this payload. Now what it does, it is actually observing the Earth from the moon. Why? So Earth is a habitable planet. We know that in Earth there is a conducive atmosphere for sustaining life. So it is always viewing the Earth from space, not from Earth orbit, from space, and getting the signature of a habitable planet from the space. Now, how can we use it? We know that there could be some exoplanets in which life could be conducive elsewhere, not in the solar system, but elsewhere. So, if Earth is giving out certain signature of life in the form of some manner, in the form of some radiation or some other parameters, This shape will analyze those. And now, if we look deep into the space, we will try to get, through some other payload, we'll try to get similar signature from some exoplanets to identify whether there's a possibility of life there. That is an important, interesting payload called SHAPE. So let us see now the operations or the locations of those payloads. So this is where the chassis is arranged on the lander. We'll see the animation of operation later. And this is where the REMPA or the Landwehr probe is placed. And this is where the ILSA or the seismic activity measuring payload is placed. What happens is this will not remain here. After landing, this particular payload will be dropped to the lunar surface through a controlled arrangement. And this payload will come into contact with the lunar surface, then it will make some measurements. Now, this is the laser retroreflector array. This is actually supplied by NASA. This will accurately measure the distance from the Earth. From Earth, we will send a laser. So this will reflect the laser back and that will be received. And based on the time taken for sending to receive of the laser, we can accurately find out the distance. And this is the payload for the equipment for measuring the lunar phase. So now this particular thing, this is how, sorry. Sorry for this. Okay. This is how the chassis payload comes into operation. So it is initially locked onto this one. So initially it is rotated and deployed like this. And now it reaches around some height above the lunar surface. And then one probe is inserted into the lunar surface like this. And this is inserted inside the lunar surface. So we get the temperature estimates of the lunar surface. And we were in fact thrilled to see that at the surface of the moon, we had a temperature of around more than 50 degrees centigrade. But when we went 100 mm inside, the temperature became minus 10 degrees of the total. So that much temperature difference is there, just from the on the surface of moon and 110 centimeter inside. So if you dig a hole of 10 centimeter inside the moon, you'll find a very low temperature. And this is how the Landwehr probe, you can see one small spherical dome kind of a thing here. That is called Landwehr probe that is deployed to the lunar surface. And there it would measure the presence of any charged particles, electrons or ions like that. And this is the laser reflector array that we told. Now, we had mentioned that in Rover also we have two payloads. And one is this laser-induced breakdown spectroscope, and another one is this APX. Now, alpha particles. The details of this are always available on the internet. So if you are interested in finding more details, you can just go there and see. Let us not waste time on this. So these are the different payloads. And now, this is the photograph of lander taken by the camera on the rover. You can see this particular thing, now a small rod kind of a thing taking into the surface of moon. This is the payload chassis. And you can see one small object lying on the surface. That is ELSA. It was here where it was landed. Then we dropped it here and it made contact with the lunar surface and it measured lunar seismic activities. That's how it did. And to the question that Vasant asked earlier, what is he doing now? What is our lander doing now? Now, our lander and rover are in deep sleep because they are here. And today, the moon is here compared to Earth and Sun. So the location in which our lander is, unfortunately, now not under the sun. So it is night. It is night there and in deep sleep. But we have set him an alarm on 22nd of September when he is supposed to be here. So it will be an early morning for him there on 22nd of September, and we have kept an alarm. And let us hope for the best that he will wake up to our alarm. Thank you.
Thank you, sir. That was very helpful, and we got so much information from you today. I think, kids are also very much interested in this topic, and they were eagerly asking a lot of questions, and we have to stop the chats from coming in. And so that's how, discussion was happening. So it was very wonderful to see such young, children getting engaged in such, innovative and advanced topic, and also, continuously asking you questions and following up with you, and getting into a conversation. So that's very, nice to see from my end, and really thanks for you to, take time and joining us and helping us to get some useful information about Chandrayaan 3, and also inspiring a lot of kids here. So on an ending note, I want to ask you, like, what is that you want to say to these kids that who have joined enthusiastically today to learn more about space tech? What do you think they have to do to probably develop a career in space, or get into this direction? What are your thoughts on that, sir?
Dream and keep on dreaming. See, right now you are kids studying on fourth, fifth, or sixth standard. It's very good and it's very nice to develop enthusiasm on subjects like this and to learn what are possible. But at the same time, try to do best on what you're supposed to do now. You are not supposed to learn a lot of subjects. Believe me, all the subjects that you learn will benefit you in your life. So work hard and learn whatever you have to learn right now in a best possible perfect manner. At the same time, develop enthusiasm, gather information about these kind of activities from all around the world. At the same time, be an expert in your area in which you are now. Learn. When you grow up like that, there will be in a point in your life where you will be allowed, or where you will be where you will be allowed to take decisions about the career in life in which you go. At that point, you will be able to take a decision of your career and towards space or towards any other area. But right now, you need to concentrate on your studies and to be as good as possible in that, while getting an overall awareness of such kind of things happening around us. And keep on asking questions. You bombard your parents with questions. Let them also learn and teach you. So keep on asking questions of whatever you see, observe, and or you may have imagining that one day sun is rising from one direction and you get a shadow in this direction. After 6 months, you get shadow from some other direction. You ask people why. You start observing everything that we see. That will give you a lot of wonderful answers also, and you get to know more about the physics and the other scientific aspects behind it. Thank you.
Yes, sir. That's a wonderful answer, sir. And adding to it, I think what you said is very true. Where kids need to explore a lot of things, and space is a very vast field. So it's just that you have to be an expert at one particular direction to actually succeed in space tech. But there are certain common skills that we found that is very important for kids to excel in the coming days. Probably they are like critical thinking, creativity, right, innovative mindset. So these are certain skills which kids can develop to step up into their profile and develop a good career in space technology. And once again, thank you, sir. On behalf of all the kids, from my heart, I thank you for taking time and joining us today. So we thoroughly enjoyed the session. So for kids in the Zoom meeting, and who are watching it live at YouTube, please do subscribe to our YouTube channel to get more as such Playto Talks, and get useful information on how our current technology is advancing and how experts at today's world is helping us shape up the future. So once again, thank you, sir. Thank you for joining, and I hope everyone liked the session today. In case children, you have questions, you can ask your Plato teachers, and I'm sure your Plato teachers also will be able to help you with the questions, with the answers. And in case you have some other questions which you want to ask Mr. Shiju sir, please do send us a WhatsApp or an email. Certainly, I would run it through sir when he has time, and revert back to you with the answers. So thank you everyone for joining. Thank you, sir. Have a great day ahead, all of you, and have a fun time today. Yeah. Bye bye,
Thank you.
everyone.
It was nice to be with you, and it was nice to be interacting with the kids in this manner. Okay, so thank
Yeah.
you.
Yeah.
Thank you. Bye.
Yeah. Thank you, sir. Thanks for this, sir. Thank you, everyone. Thank you, parents. Thank you, kids. See you in the next Plato Talk.